Okay, so here's the second part of the in-class portion of the combo of sections 7.3 and 7.4. So picking up where we left off, the equation of the unit circle is x squared plus y squared equals 1. We can take that equation of the unit circle, and if we replace the trig definitions that we learned earlier in this section, we know that the sine of theta is y and cosine theta is x. If we replace those definitions, we replace x with cosine theta and y with sine theta, we get that cosine theta squared plus sine theta squared equals 1. Now, we can write cosine theta quantity squared. We can abbreviate that sort of. I mean, we say abbreviate, but I mean, it's instead of writing this parentheses, we can just put the squared right here. Now, you want to be careful because if you don't write the parentheses, then it looks like you're squaring the theta. And you're not. You're squaring cosine theta. So it's cosine theta times cosine theta, as opposed to cosine of theta times theta. So to avoid that confusion, we can put the squared right here. So this means the same thing as this. All right, so, oh yeah, hey, look, I just said that. It's like I knew what I was going to write. So that means that we can then write sine theta quantity squared as sine squared theta. So we get that the unit circle equation of x squared plus y squared equals 1 can be rewritten as cosine squared plus sine squared equals 1. That's what's called a Pythagorean identity. Now, is that related to the Pythagorean theorem? Heck yeah, it is. I mean, look at the unit circle. We know that's the radius of the circle, which is 1, because it's a unit circle. And if we, it goes through that point x, y, so if we drop that perpendicular straight down, that distance is y, that distance is x, that's a right angle, that's a right triangle. And the Pythagorean theorem says that the leg squared plus leg squared is hypotenuse squared. So x squared plus y squared equals r squared. And we just said that x squared was going to be cosine squared, y squared is sine squared, r is 1, 1 squared is 1. So yeah, that's called a Pythagorean identity. Now, there's actually 3 Pythagorean identities. There's this one, and then there's 2 other versions of these. So this is on your formula sheet. These other 2 versions just come from a little algebraic manipulation. If we take the Pythagorean identity of cosine squared plus sine squared equals 1, now you can write cosine squared or sine squared first. It doesn't matter because addition is what we say cumulative. So it doesn't matter which one you put first. If I take that original Pythagorean identity and I divide every term by cosine squared, this first term becomes 1. This, remember sine over cosine, that quotient rule, that's going to be the same thing as tangent. So sine squared over cosine squared is tangent squared. And then 1 over cosine was secant, so 1 over cosine squared is secant squared. Just for the record, I know I get kind of lazy sometimes, and I'll say things like cosine squared plus sine squared equals 1. I do know that there's a theta there. I'm just kind of lazy sometimes, and I don't always say that. I don't always say cosine squared theta plus sine squared theta equals 1. So just know that if I don't say it, that it is understood to be there, and it's just, me being kind of lazy there. Then we have cosine squared plus sine squared equals 1 again, but this time I divide through by sine squared. If I do that, remember cosine over sine, that's one of the quotient identities there. Cosine over sine is cotangent. So cosine squared over sine squared is cotangent squared. This becomes 1 because it's something over itself. And then remember this is a reciprocal identity of 1 over sine, which is cosecant. So 1 over sine squared is cosecant squared. So I want you to be able to derive these 2 formulas on a test. So if I ask you to use this Pythagorean identity and derive one of the other 2, this is what I'm looking for. So I just want you to know that that's something that could be asked of you. Okay, so looking at that Pythagorean identity, we know that sine squared plus cosine squared is 1. Those angles must be the same. All right, so sine squared theta plus cosine squared theta is 1. Those angles have to be the same measure. If that's the case, it does not matter what they are. It doesn't matter if this is 30 degrees and 30 degrees, 60 and 60, or 953, 953. If those are the same, then sine squared plus cosine squared is 1. What about cosecant squared, pi over 16, minus cotangent squared, pi over 16? Now this is an algebraic manipulation of one of the other Pythagorean identities. And let's see, this one's got cosecant squared and cotangent squared. So we have this third Pythagorean identity of 1 plus cotangent squared is cosecant squared. Now this is going to be the same thing as 1. Why? Well, let's look at the original Pythagorean identity. We had 1 plus cotangent squared equals cosecant squared. I'm not going to divide. Remember last time I divided all the terms by something. Here, if I just subtract, because that's a plus, if I subtract cotangent squared from both sides, that zeroes off, and I get 1 is equal to cosecant squared theta minus cotangent squared theta. So not only are there 3 Pythagorean identities, there's these algebraic manipulations of them, where you can add and subtract terms across the equal sign. So cosecant squared minus cotangent squared is 1. All right, so let's do some approximating using the calculator. Just break out your calculator, pause the video, and do these along with me, because I want to make sure that you can use the calculator. All right, so first up, that's degrees. So you need to make sure you're in degree mode. So we're going to hit the mode button. And you can see, for me, it's the third line down. I have radian and then I have degree. Degree is highlighted. If radian is highlighted, then you're going to use these arrow keys here. You're going to arrow down over to degree, and you're going to hit enter to highlight it if it's not already highlighted. So I'm going to get out of the mode by hitting second and then mode, which is the quit button. All right, so sine 400 degrees. All right, so that's approximately equal to 0.64. Cosine of 0.6. Now there's no units on here. That means it's radians. So don't just type in cosine 0.6 right now, because I'm still in degree mode. So I need to go back to my mode, arrow down to where it says radian, hit enter to select radian measure. Now cosine 0.6 is about 0.825, or about 0.83. The next one, the cotangent of pi over 18, you don't have a cotangent button. That's okay. You know the cotangent is the reciprocal of the tangent. You could also do it as, as the quotient identity. The word left me there for a second, sorry. Of cotangent being cosine over sine. So if you wanted to do it that way, you could. I just chose to do 1 over tangent. This is in radians because you don't see a little degree symbol. So 1 over the tangent of pi, that's not pi. That's what I get for trying to do this without really looking. Okay, pi over 18. Now when I say over, I'm doing this division for that. Use the pi symbol. Don't use 3.14. Use the pi symbol. You'll be more accurate that way. All right. So then we get about 5.67. All right. And then lastly, secant 25 degrees. That is a reciprocal function of 1 over cosine 25 degrees. That's a degree mode, so I do need to go to mode. Go back to degree here. All right, so 1 over cosine 25 degrees. And that's about 1.10. Okay, so the circular function definitions require that we use the unit circle, which is r equals 1. If r is not equal to 1, we can use similar triangles to rewrite the 6 trig functions. Okay? So here's what we're going to do. The sine of theta, it was just y. But if we look down here, we've got the unit circle. let's say that the point we're looking at is not on the unit circle. It's just on some other circle. That unit circle triangle and this larger triangle here are similar. Now, I don't know how much you remember from geometry, but they are similar by angle, angle, angle. You know, they have this shared angle right here, that right angle, which makes this upper angle right up here be the same. If they're similar, then their sides are proportional. All right? So that means that the ratio of y1 to 1 is the same as y to r. So we get that the sign can then be, that definition can then be kind of expanded upon. Instead of just saying it's y over 1, because we had the unit circle, now we can just generically say, hey, it's just y over r. The cosine, instead of just being x, because it was x over 1, you know, because the unit circle had a radius of 1, now we can expand it to, you know, any circle and say, hey, it's x over r. Tangent, still y over x, it's independent of the r value there. And then we get our reciprocal functions, you know, where the cosecant is just the flip of that, the secant, just the reciprocal of cosine, and then the cotangent is the reciprocal of the tangent. All right, and this is the stuff I was saying earlier about how the triangles were similar by angle, angle, or angle, 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 whichever. This means the ratio of their sides are equal. Okay, so if P is a point on the terminal side of an angle, let's say theta, find sine theta and cotangent theta. Now I'm just giving it a name of P, and I'm telling you that the coordinates are -3, -4. Okay, so let's plot that point. So -3, -4 is back here in quadrant 3. The terminal side of that angle is going to be coming through here, through quadrant 3. We know that the angle's in standard position, so we know that we got that initial side happening over here, and that vertex on the origin. So there's my angle theta. Now, I have right here that r is equal to 5. Where do you think I got that from? That wasn't said explicitly in the problem here. So how do I know that r is 5? Well, I know that the equation of a circle is x squared plus y squared equals r squared. That's from the equation of the circle and from the Pythagorean theorem. Those are connected. So my x value of that point is -3. My y value of that point is -4. And those are quantity squared. So you're squaring the negative and the 3. So we get 9. Squaring the negative and the 4. So we get 16. So that's 25 equals r squared. So r is normally plus or minus 5. But because we're talking about the radius of a circle, it's just going to be the positive. So we have from our point that it's -3, -4 for x and y. And then from the Pythagorean theorem, or from the equation of the circle, we get r equals 5. With all of these, now I can just go back to the circular function definitions. That sine is y over r, so y over r, and cotangent is x over y. So x over y. And then this simplifies. That negative over that negative is a positive. Alrighty. Last one. Given that tangent theta is -2/3 and cosine theta is positive, that's what greater than 0 means, find and simplify the exact value of sine theta. Now, here's the kind of stuff that you need to take away from this. You need to say, hey, the tangent is negative and the cosine is positive. So that's whispering those sweet nothings into your ear and saying, hey, we're in quadrant 4, bro. All right? So we have that tangent theta is -2/3. We know by definition that's y over x. But, here's where that quadrant's going to be important. -2/3 is the same as 2 over -3. It's just more standard practice that we put the negative on the top. Because if that negative had been on the bottom, I mean, it'd be the same thing, but we just kind of, typically write it on the top. So how do I know if it's negative 2 and 3, if negative 2 is your y and 3 is your x, or if 2 is my y and negative 3 is my x. So which one is it? Well, if y is negative 2 and x is 3, I get the point 3, negative 2. That's in quadrant 4. If y is 2 and x is negative 3, I get the point negative 3, 2, which puts me in quadrant 2. This up here told me, hey, you're in quadrant 4. So I know I'm going to use this one. All right, so this is the quadrant 4 one. So this one we are not going to use. That means sine then is y over r. From this point, we get that y was negative 2. I don't know what r is, so I kind of went off to the side here and did my Pythagorean theorem. X squared plus y squared is r squared. So I get that 3 squared plus negative 2 squared equals r squared. 9 plus 4 is 13. So r squared is 13, so I take the square root of both sides. Don't have to do the plus or minus. So I get r is root 13. So the sine being y over r, my y value is negative 2. My r value is root 13. I do need to rationalize this by multiplying by root 13 over root 13. So I get this more simplified answer of negative 2 root 13 over 13. Okay, so that concludes the second part of the in-class portion of sections 7.3 and 7.4.